So we divide the computer architecture into the two format in terms of the what kind of memory it would use. So what kind of, so if for both instruction and data we use the same memory, and the memory would interact with the processor or central processing unit. So if these two memories are in one single chip, then we call that computer architecture as a von Neumann computer architecture. On the other hand, we have another kind of computer architecture we call Harvard architecture, which it has a two separate memory, one for instruction and one for data. Okay, so the current advanced microprocessors would use Harvard architecture. Okay, the reason is that because at the same time the program which is stored inside the instruction memory can be read, or we call it fetched, to the processor, and then it will be interpreted, and then based on what kind of program, then the corresponding action should be done by the processor. And then sometimes one action would be reading to the memory or writing, reading from the memory or writing to the memory. And at the same time, then it could perform both operation on the data and then the reading from the instruction. So that introduces some kind of parallel processing, which improves the performance of the microprocessor in the Harvard architecture. Whereas in the von Neumann computer architecture, you can have only access to memory at one time. So that location of the memory would be either data or would be instruction. So you cannot access at the same time for both instruction or data. So the old microprocessors would be von Neumann, and the recent would be Harvard. Sometimes this kind of microprocessor, since it has a lower complexity, is cheaper to fabricate for some applications. For example, your appliances doesn't need that high performance to be very fast. So in that case, the price would be very important, because that kind of appliances would be produced in the mass production, and then the price would be very, very important, more important than the just performance. Okay, so let's see, go into the details of inside the computer architecture. Let's talk about the von Neumann computer architecture. So some computer architecture as shown here, inside the processor, or we call it central processing unit, or CPU, has three main units. One is going to be the control unit. The next one would be arithmetic logic unit, and the next one would be register. Okay, so let me talk about the outside. So as I mentioned before, the von Neumann architecture has one memory for both instruction and data. So, and the memory should have one address which refers to the specific location of the memory, and the data would be what is stored in that location. So, and for the von Neumann, both instruction and data would be the same. Okay, and then some computer architecture should have a I/O, or input output peripherals. So, and inside the input output peripherals, it has some memories, and in order to access those memories, it requires address and data. So, for examples of the I/O peripheral would be keyboard, 7-segment display, monitors, or depends on what kind of application or timer we have. So we have the different I/O devices. Okay, let's come back to the inside of CPU or processor, and as I mentioned, the control unit would be just interpreting the actions, the instruction code, and performing the action. So the CPU, the codes, I'll explain more details later on, but the codes are stored into the instruction memory, and when the instruction memory would be executed, the machine code of that instruction would be fetched or would be loaded inside the CPU. So the data, which is a machine code, which is instruction, would be loaded into the control unit. And then based on that bit patterns, the control unit understands what kind of instruction it would be. So it's designed, each unique instruction would have just unique operation. So for example, if the instruction would be adding to register, then after fetching that instruction, then the control unit, it has a finite state machine inside, and that finite state machine interpret that opcode or operation code, and then based on that operation code, it performs the corresponding operation. So if that instruction is an addition operation, then the part of the addition hardware inside the ALU would be activated, and then it performs some action. So for example, if the instruction would be adding the 2 registers, we have the CPU usually have several registers. Each CPU has a fixed number of registers, and registers, as you know from the digital logic course, would be locations of the memory, a bunch of flip-flops that store data, but as compared to the memory, the registers are much faster than the memory. So, and then when that instruction would be adding of 2 registers, then the control unit some kind of perform some actions, and then directing these 2 registers inside the ALU, and then performing the addition operation, and then the result would be stored in another output registers. Okay, so and then for example, if that instruction code would be just writing a digit on the output devices, for example, the 7-segment display. So in that case, that 7-segment display is a location of the memory. It has address, and then the corresponding address would be provided to the that address input of output devices, and the data for that numbers would be provided to the data input of that output device. So you can, as you can see, that for the von Neumann computer architecture, we have just a single address bus for both memory, data, and I/O devices, and we have a single data bus for both memory and I/O devices. So we refer as a bus as a number of bits. So each bit would be either 0 or 1. So, and then a bunch of the bits, we call it the bus. So, and then we have different bus that would be either data bus, which contains the data. If some value would be in the output of devices, peripherals, then that would be data, or could be the instruction code or matching code, or sometimes your code requires just storing some data in the memory and use it for some further processing in that code. So that data would be actual data. So we have another kind of a bus, which we call it control bus, and that control bus is missing in this computer architecture, and those control buses would provide different actions. For example, if you have a memory, then whether you are going to read from the memory or write from the memory, then one input should be activated, whether read or write. So we'll talk about memory later on, as I mentioned. And similarly, we have different control signals, and then the collection of those control signals, we call it as a bus. Let's come back to the central processing unit. So we talked about the opcode, which would be based on the bit patterns. Then the operation code would be entered here. And for example, if you are adding the 2 registers, the result will be obtained by the arithmetic logic unit, specifically the adder part of ALU. And then some flags, as I mentioned in my previous lecture, would be inside the ALU: carry flag, overflow flag. Those are the 2 main flags, and we call those as a status. Some register inside the CPU or ALU would be the status register, which indicates whether you are having a carry, you are having an overflow as a result of operations. And then you can, the ALU, the output of ALU would provide the result into the register. So this is going to be a brief introduction of the von Neumann computer architecture. And then when you come back to the Harvard architecture, you can see that the differences between these two would be, we have separate memories. One would be instruction memory and the other would be the data memory. As you can see that the instruction, when we separate them, then the address for the instruction memory would be different. The address bus for the instruction memory would be different than the address bus for the data memory. And usually IO prefer we refer as the data. So the data for these two blocks would be connected to the common data bus, and that would be bidirectional. So you can read the data from the IO preferer. For example, if your data would be just a switch, you will see it in the lab. So if you have a dip switch, and that would be the input data. So it would be read inside the inside of the processor. Sometimes you want to display the result in the 7-segment display, then 7-segment display would be your output device. So in that case, the data would go to that location. So and then sometimes you want to read from the data memory. So in that case, you can see that we have a shared address bus between IO and the data memory, and we have a separate address which would be for instruction, and the instruction code are stored in the different locations of the instruction memory. And then you can see that when the instruction code is stored there, and always the direction from the instruction code would be inside the to the CPU. So when the CPU read the data instruction code and then perform execution of that instruction, then it goes to the next address and so on. So for ARM the processors, we have a different chips. So these are the ARM processor within von Neumann computer architecture. So the early processors would be the ARM, or cheaper in terms of price, and the hardware would be more advanced. And these are the different instruction sets. We will talk about the instruction sets later on. So we'll be using ARM v7 in our lab instruction set, and the ARM v8 would be next generation after v7. But most instructions between these are common. So we will talk about them later on.